dopoledne. Vítejte na dalším čtvrtku ve Viničné a než vstoupíme k představení dnešního hosta, tak jako vždy poutat na příště. Příště bude unikát, dneska to bude zoologie a bude to město na hraně spolupráce nějak, bude to prostě o unikání a zanikání eusociality. Takže určitě se máte na těšit. Now I'll switch to English and I'll pass forward to Alice, who will introduce today's guest.
Yeah, thank you so much and thanks everyone for coming in this horrible downpour outside. And just a few words about our today's speaker. First, I would like to thank Tom for making time to come to Prague and give this talk. And just a brief introduction, Tom did his biology studies first in Edinburgh and second at Dundee, I guess. Yeah.
Dundee,
and then,
yeah.
Then he moved to Canada and established his laboratory and team at Carleton University in Ottawa. And he's got quite a broad evolutionary biology or biology interest, spanning from evolution of cooperation to adaptive values of superstition. And one of his topics, I will maybe the main one of interest, is anti-predator interactions and anti-predator strategies, which will also be his topic for today. And within this, as you could see, he just did just about everything, starting from camouflage to mimicry, warning signaling, daymatic displays. And what I particularly like about his approach is just that he always tries to combine theory, comparative approaches and experiments. Tom, we are all waiting for you.
Yeah. Thank you very much, Alice, and thank you for hosting myself and Catherine while we're here for me for a week and Catherine for a month. I'm going to be talking about threats, bluffs, and conjurers' tricks, and the variety of ways animals can signal in order to avoid being eaten. So to begin with, I'm going to be looking at threats, and in particular focusing on hidden warning signals. I'll be looking at how they work and also how they might facilitate the evolution of permanent warning signals. So instead of being facultative, they're actually permanent. I'll then go on and consider a related topic, and that is the topic of bluffs. Now, bluffs is a very big subject, and so I'm going to be focusing on one particular form of bluff, and that is the evolution of eye spots. And I'm going to be looking at how eye spots work to deter predation, and why only some species seem to evolve them when it seems to be a relatively beneficial trait to have for all. And then finally, I'm going to be looking at conjurers' tricks, in particular how prey can seemingly vanish in front of your eyes. And I'm going to be then using that as a jumping board to look at how organisms might evade predation by simply being fast movers, and how they could signal that ability, and also how those signals could be exploited by others which are actually a little bit slower moving. I've got several consistent themes, and the first one I'm going to be introducing to you a whole series of experiments to look at properties of these defenses to see how they work. And then, as Alice introduced, I'm really into mathematical modeling, and so I'm going to be giving you an idea, without going into too much depth, an idea of how we can use mathematical models of cognition, particularly based on Bayes' theorem. Bayes' theorem is a very simple means of combining probabilities, and I'm going to go over that a little bit later. And we can use mathematical models to help us understand some of the observational data that we make. And then I'm going to be looking at phylogenetic analyses. I'm going to be looking at the evolution of these signaling traits within whole trees to test trait associations, but also how the defenses might evolve in whole groups. And then finally, and I think this is really important, I'm going to be talking about controversies, because it would be very boring if there were no debate around how certain defenses work. And so I'm going to try and highlight alternative views and try and give you my impression of why certain views are likely to hold over others. But please bear in mind some of these topics are somewhat debated. So, the first topic is that of threats. Many species are cryptic at rest and yet display a conspicuous colour pattern when they're approached by a would-be predator. Here, for example, is a moth. We get a lanternfly. When approached, they can signal in a very conspicuous way. Signalling is often done when those prey species are stationary or moving slowly. And I thought I'd show you some examples. Here's this one example. Oops. Let me see if I can. This is a lanternfly, and this is what happens. Typically on touch, it signals somewhat non-startlingly to a human, but it may well have an effect on a would-be predator like a bird. Here is another example. This is the mountain katydid, studied by Kate Umbers, and what we can see that typically on contact or very close proximity, the katydid will reveal these highly conspicuous colours. Now, you may think that they're not really that frightening to humans. I just want to show you what certain signals can do when birds see them. And let me see if we can get this. So this is domestic fowl, and it's actually a peacock butterfly here, but the peacock butterfly has been blacked out here, and you can see that when it opens its wings, it doesn't really do anything. And yet, here, the eye spots are actually visible, and you can see that it is significantly concerned about those signals. In fact, in many of these cases when they ran these experiments, it was actually forming alarm calls, predatory alarm calls, when it was startled by those individual signals. So, here's a question. If startle displays provide an effective backup defense, why do some species have hidden signals, but others do not? And we started to address this question about 10 years ago, and this is work that I've done with Chang-Hu Kang, who's now in Seoul in South Korea. And we decided to look at a rather large family, the Erebidae, which includes some really very interesting signalers. Here are the Catocala moths. Not all Catocala moths have signals, but many of them are well known for their hidden signals, which typically display when you get really close or even sometimes have to touch them. So, moths, in this case, can be objectively classified in terms of whether their forewings and hind wings differ markedly. This one doesn't, and this one, I hope you will agree, will. So that's a low contrast, and that's a high contrast. And you can simply go through as many species as you can with image analysis and actually classify them in this very simple binary way. And you'll see a whole bunch of high contrast individuals, and here's a bunch of low contrast species. Now, important to note, every moth has its story. Every moth got there through a whole series of transitions from species to species, natural selection. But the question that we wanted to ask is whether we could detect any underlying patterns. Was there something about these which was different from these? And the answer was a very simple one, that overall the contrasting species tended to be bigger than the non-contrasting species when we control for the phylogeny within the Erebidae. So that's something quite interesting. We thought it might be a one-off, but then we decided to look at other species groups. And with Carl Lafleur Henry, who was my PhD student at the time, we looked, for example, at mantids. Mantids show exactly the same effect when you control for phylogeny. The larger mantids are those species that tend to signal overall. And here are Orthoptera. There's the hidden contrasting and there's the non-contrasting. And again, there's a significant indicator that the larger species are the ones that tend to have those hidden signals. There was just one case where we didn't find it, and that was in the sphingids, like that. Okay, so here's a hypothesis, and you may have come to this already because you may think it's quite obvious. Maybe startled displays in large insects are more effective in deterring predators than startled displays in small insects. Here's the idea. This is scarier than that. So we decided to put this to the test. And Chang Ku, while he was working with me in Carlton, managed to recruit a robotics, an electrical student that was interested in robotics. And we built a Bluetooth-controlled moth that would open up and maintain its wings and then put them down. It would react very quickly. And all we had to do was find some birds and scare them by opening the robo-moth and getting it to close. Here's the design. We decided to look at small moths, artificial moths, of course, that open their wings. And I should say that they're baited with mealworms. So here the chickadees would come down looking for the mealworm, and then the wings would open, and they'd either get a highly contrasting signal or a non-contrasting signal, and they'd either be small or large. And we managed to replicate on the flock basis. This is wild populations. We'd go to, I think we went in the end to 36 flocks of chickadee with 9 reps for each of those. Now, some really interesting results here. I'm going to show you some videos. This is just giving you an idea of the least startled to the most startled. You see it's not very impressed by that at all when it opens. There is jumping a little. Here, there's more of a spook to it. And then finally, the most startled was a lot of events like that. It would open up. So, what did we find? Well, this is what we found. When they were small, it really didn't matter whether it was contrasting or non-contrasting. They really didn't really have much effect. There wasn't very much difference. And yet, when they were large, the contrasting moths tended to have 100% survivorship of the mealworm that was associated because they were so spooked, whereas the non-contrasting moth had a far smaller effect. It's only around 50%. So a big effect of the startle signal, but only when they were large and not when they were small, which is consistent with the idea that big things, when they open their wings, are scarier than small things. Why are big things scarier? Well, probably because they're more likely to harm you when they open. When you look at a small thing, it's not much of a stimulus as it's being released. So, it's most likely in this case that sudden reveal of a colour isn't really a threat, it's more of a startle. So it's just changing the view of the bird momentarily, and it's thinking whether it should flee or not because of this momentary distraction. And recently with Alice and some co-workers, we've been looking at the cognitive ecology of surprise. And I'm not going to go into detail, but here is the example from Chang Ku's experiments. You can define surprise in a behavioral way as a mismatch between an animal's expectation and what it observes or experiences. So that's what you can do in a qualitative way, but it's much harder to actually work with than a quantitative definition. And so we adopted a quantitative definition which is based on Bayesian surprise. It's how an organism's belief is modified by new observations. And I'm not going to go into any detail, but if you observe something and it doesn't change your mind at all about another property, X, then clearly you're not surprised at all. And with this, Olivier, our co-author, Panchero, I think, worked out the Bayesian surprise involved in this. I'm not going to go into detail, but it was based on neural stimulation, etc. So, and of course, the problem with surprise is the more information that is gained, the less surprise there is, especially if we follow this type of definition. And this is what happened with the moth experiments that we conducted. Here is the survivorship, and here are the different treatments. That's the small non-signaling all the way up to the large contrasting like that. And I hope you can see the small non-signaling, it waned off pretty quickly. There might have been an initial relatively high survivorship, but it waned. And yet the large contrasting tended to be maintained for somewhat longer. So habituation arises, but it's slower for those larger flashes. I'm going to show you some examples of habituation, but not spend too much time on it. This is work done by my colleague, Jane Yack, at Carleton. I hope you can hear it. No, you can't. It's a whistling caterpillar. If you listened, there might be a little hint, but I just want to show you what happens to red-winged blackbirds, and this was conducted at Queen's Biological Station, on the first exposure when they're coming down, and it's the sound, they're spooked. But it doesn't take long before this happens. They're not spooked at all. So, we became rather interested in that from a variety of perspectives. And one perspective that we had was approach latencies to approach unfamiliar prey. And one thing that we noticed in this experiment that we did, I should explain, this experiment was based on the Canadian swallowtail, Papilio canadensis, because it looks a little bit like a snake. It's got eyes, but it's also got a swollen head, which when approached will actually swell its head even more. And we did some experiments a few years ago where we wanted to look at how chicks, domestic chicks, would react to the various traits that are there. And here's the swollen head and eye spots. And here is no swollen head and no eye spots. And here we've got eye spots but no swollen head. And there we've got the swollen but no eye spots. So we've got all four combinations. And what we found is that here's the latency. There's individual chicks over time. They're only given one treatment. Here are the chicks for this treatment. It didn't decline very much, but it did decline. Whereas these, which only have one or no individual signals in common with these, decline rather quickly. So you can maintain the latency for longer when it's a multi-component signal rather than a signal which only has one of the component or one of the components or none of the components like that. So some stimuli were habituated too quickly and other stimuli were habituated too slowly. And this turns out to be quite a common phenomenon in psychology. The weaker stimulus, the more rapid the habituation. And strong stimuli, sometimes there's no habituation at all. So, very recently, and this is just over the past year, I returned to this particular problem to try and understand it. And I decided to fit a Bayesian model to try and understand that approach latency, what was in the chick's mind. The longer you wait without being attacked, the more likely the object is harmless. So if you're a chicken with an individual strange thing in front of you, the longer you're waiting and it's not attacked you, the more likely that that object is non-threatening to you. So that's the first bit of Bayesian updating, and it's continuous. Then there's a second piece of updating, because here are consecutive trials on 3 separate days. The more trials in which a prey type is edible, the more likely all such items are edible. You have the first, oh, it turned out to be edible. Then you get the second, and you learn a little bit more. Okay, more and more of these items tend to be palatable, and eventually you'll work out that they're all palatable. So there's two forms of updating. You can actually combine them, and if you make some simplifying assumptions, you can actually predict the optimal time to approach an unfamiliar object. And it involves your perceived conspicuousness, if indeed it was a threatening predator. It involves the cost, if it was, which is probably very high, the benefit if it's not, if it's a nice prey item to eat. Here are your priors. This is alpha and beta, and this reflects your prior beliefs about the nature of that object. And here is n, that's the number of trials there. Of course, I'm not going to try and derive that, but you can actually fit that model to the observed data, and you'll see that the fit is quite good. It's not proof, but it allows you to measure some of the parameters. And here's our estimates. If the model is correct, here is the best estimates of the prior beliefs of chicks when the object is non-threatening like this, is resting position and no eye spots. So it doesn't really know. It could be threatening, it could not, and then it's like that. Whereas here are the prior beliefs for the more threatening object, where it's got a swollen head and eyes. It's like that. So, the more convinced you are that an unfamiliar object is dangerous, the lower the rate of habituation. We already see this. But this method allows us, if we assume a certain model of the world, to back estimate the priors, what it should have had, for it to be most consistent with the observed data. Okay, I said that there would be some some controversy. Here's the really weak controversy, and it's not much. When papers started to come out on these so-called startle or threat displays, and by the way, that term is dematic, people wondered whether some of these displays might actually be honest signals of some form of chemical defense. And the debate centered on this species here, the mountain katydid. So the question arose, are those signals, or those hidden signals, a bluff or an honest signal? And my answer to that is, I don't really care, because the signals provide some defense to the organism, and I'm sure in some cases it's a pure bluff, like in Catocala, they're thought to be palatable. And so they only gain through the startle mechanism and nothing else. And yet, in other cases, it's well known that those signals, those hidden signals, when made, are actually honest. And it tells the predator not to proceed. So sometimes those hidden signals can serve to startle, and other times they can serve to indicate unprofitability. But here's the thing. And the thing is this, that many warning signals aren't facultatively displayed, they're permanently displayed. And they're displayed, here for example are wasps, we've got millipede, and of course there's lots of examples of butterflies. They're displayed to indicate some form of unpleasantness or unprofitability. The term that we give of the association between bright colours and unprofitability is called aposematism. I'm sure most of you have met that term. It comes from Edward Poulton. But there's a problem with the evolution of aposematism that has been recognised for a rather long time, from back in the 1930s. How can a conspicuous mutant spread in a population of cryptic, unprofitable prey? So let's say they're all unpalatable, but they happen to be hiding. How can that first mutation, that conspicuous mutation like this one, arise? It faces a double whammy. The first is it's more conspicuous than its conspecifics, and the second one is not as readily recognized as being unprofitable. And so it might be a really hard thing for those initial mutants to spread through natural selection. Of course, over the years there's been a number of explanations, and here's one explanation that has recently been receiving quite a lot of interest. It's so-called receiver bias. maybe there's something about these conspicuous forms that not all individual mutations are treated equally. Maybe predators have evolved prior dispositions to learn about conspicuous signalers when they're unpalatable. Maybe they'll approach them more cautiously and handle with care. So this is the basic idea, that maybe those conspicuous mutants already gain some advantage because the predators are sort of primed to be much more careful with warningly coloured prey. And it's something that we, and including Alice and Anita and Catherine here, are beginning to investigate right now. What we're doing is looking at the reaction of birds to unpalatable prey with cryptic and with novel conspicuous stimuli. And the idea here is to estimate the Bayesian priors, the way they learn about how unpalatable they are and how quickly they learn will allow us to back estimate the Bayesian priors involved to learn something about the effect of those signals on individuals that have not seen them ever before. But there's a second solution, and the second solution is this. Okay, the typical way warning signals are presented are, we've got cryptic individuals, how on earth will it evolve aposematism? Well, of course, a relatively obvious solution now that people are becoming more aware of hidden signals is that maybe hidden signalers could provide a stepping stone towards the evolution of full aposematism. And it works great mathematically, but many things work great mathematically and don't necessarily explain the world. But here is a simple replicated dynamics model where we've got cryptic prey giving first rise to individual prey with hidden signals, and then once those prey with hidden signals tend to do well, it paves the way for prey with aposematic signals like that. We decided to put that idea to the test, and this was a very ambitious project led by my PhD student, Carl. He looked at over 1,100 amphibia and decided to classify them according to whether they were camouflaged, or whether they were fully aposematic, or whether they actually had hidden signals on their venter, whether it's partially conspicuous or fully conspicuous venter like that. So we went through every single one, and it's not just him. We had other herpetologists going over, classifying those signals. And of course, the first thing you can do is you can put them on a phylogeny and see which are the hidden signalers and which ones are not. And then with Kang, we decided to do something even more ambitious, to look at transitions from one species to another within the phylogeny. And we fitted a whole variety of models. The most important ones are, there's the cryptic, and there's the conspicuous, or the aposematic. And we were looking at models which had direct transitions versus models that didn't have direct transitions at all. And what we found is that these intermediate models best explain the overall changes that were going on within the phylogeny. So the transitions from camouflage to aposematism in the amphibia were seldom direct. But instead, according to the amphibian phylogeny, instead arose via species with hidden signals. So it's yet another way in which aposematism can evolve. It's not necessarily direct. We get hidden signalers which benefit both from crypsis, and when the need arises, they will signal, and then somehow that will give rise to individuals that are not caught by surprise. They simply signal all the time. Okay, so that was the threats part. I'm now quite quickly going to move on to bluffs, but this will be shorter. I've long been interested in bluffs. Here is a stinging wasp. And here is a palatable fly. This is an example of Batesian mimicry. This is a particularly impressive example because here you'll see this fly is actually holding its forelegs in front of its head, its blackened forelegs, to resemble the longer antennae of the stinging wasp, like that. And it's not only predators that get fooled by mimicry. Here are just a few examples. This is the British Broadcasting Corporation. Wildflowers will be planted to encourage bees. No, that's a fly. This happened a few years ago. Wasp scare shuts Gatineau Park play areas. That's in Ottawa. No, we don't know whether it was a wasp there, but the picture they used was most definitely a fly. And here's one that Francis Gilbert sent me. This is the Honeybee pub in the UK. Clearly some artist drew it from a photograph. It's a hoverfly. But I'm going to be talking about one particular form of bluff, and we know it's a bluff, and that is eye spots, which are widespread in the animal kingdom. Why do eye spots evolve? Well, according to Poulton, who I introduced earlier, eye spots could deter attack through resembling predators' eyes. So it evokes their own predators, makes them scared, and they will back off. Here's one example, and many of these examples are a lot of fun, but this is the strangest. This is work that was done in Botswana, and they decided to paint cattle, hundreds of them, with eye spots versus a cross versus nothing. And they, over time, looked at predation largely by lions, also leopards and hyenas. And what they found, here's the survival analysis, these individuals were not attacked at all, so you'll see their survivorship is like that. Yet interestingly, these individuals had a significantly higher survivorship than those individuals here with no marks at all. Fascinating. This type of experiment has automatically given rise to a bit of a controversy. Eye spots protect, but the crosses are better than nothing. And this seems to be quite a widespread finding. Here's a finding with artificial moths put down, where they argued that conspicuousness, not eye mimicry, makes the eye spots anti-predator signals. And of course it gets picked up, and in fact a recent meta-analysis of all the experiments, and there haven't been that many, looking at eye spots, came down with the view that these eye spots are misnamed. They are actually just markings, conspicuous markings. However, there are a lot of other people that will think, no, 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 it's eye mimicry. And in fact, some go on to point out, well, there's even these sort of sparkle in some of the butterflies and moths that really begin to look like irises. Please ask about this later. I'd love to keep talking about it, but I can't. But after, I can talk more, including watchful eye research. I'm going to be talking very briefly about eye spots in caterpillars. And with eye spots in caterpillars, I am of the firm opinion that it is genuine eye spots rather than any form of just conspicuous signals, and I'll explain why. Here's one example of eye spot in a caterpillar. This is a sphingid caterpillar, and I'm going to show you. This was from Tom Hossey. I hope you'd agree that those spots there are not random. They are part of the eye mimicry. And believe it or not, there have been some researchers have doubted whether this is snake mimicry. It's like, well, it looks very much like a snake to me. Here's another reason. The first time we were out in Costa Rica, we met up with Dan Jansen, who's been doing an awful lot of work on eye spots, also convinced that they are genuine eye spots. And we came across a species that he hadn't seen in 30 years. It's this species here. It has an eye spot that blinks, which is the weirdest thing. But there's experimental data. I managed to convince a number of years ago John Skellhorn to do some experiments. He was also getting into eye spots. And we decided to present artificial prey here with or without eye spots, but we had the eye spots in an anatomically correct position versus an anatomically ridiculous position in the middle. I hope you will agree that they're equally conspicuous, and we looked at the total time to attack by a chick and also the time from the first observation to attack. These were approached really very quickly, they weren't in any way threatening, despite the fact that they're just as conspicuous as these guys. So this, to me, gives me some cause to believe that they are genuine eye spots. And before coming, I looked at another experiment that John had mentioned many years ago, and I'm pleased it's got published. It's not quite caterpillars, but it will tell you the same thing. What they looked at is the approach of chicks to triangles from different directions where the eyes were either looking at you or away. And what they found, I won't show you the data, is basically a Mona Lisa effect in that they were much scared when they were approaching and it looked like the eyes were looking at them compared to when they were looking away. And you could see a difference in those latencies. So, I'm convinced it's eye spots, and I want to ask the same question as before, and you'll see the same answer. If eye spots help to deter attack, why don't all species have them? And this is work from Tom Hossey a number of years ago. We looked at sphingid caterpillars, where we looked at the distribution of eye spots in the final instar of the caterpillars. We looked at the final instar because many of these caterpillars only develop eye spots later instars rather than early instars, which becomes relevant shortly. Well, when you control for phylogeny, again we see that the larger individual species are those that tend to have eye spots compared to the smaller ones. We complemented this with chick experiments, domestic chicks, and we found something really quite interesting. Here are the large artificial baits here, and here are the small artificial baits. Large tended to be scarier than small overall, but large with large eye spots tended to be the most scary in terms of the inspection time and time to first inspection. But if they were small, the eye spot actually attracted the interest of the chicken in that their time to inspection was really very low. So small caterpillars were more vulnerable when they had eye spots, and large caterpillars were less vulnerable when they had eye spots. So that's interesting, and it explains the general trend we see, but there's still a little bit of a puzzle. And the puzzle is that there are some cases, not many, where we see individual species with small caterpillars and they have eye spots. What's going on there? A really clever experiment by Postema quite recently wondered whether it was associated with the leaf rolling. Many caterpillars will live in leaf rolls. Now, she's not done a phylogenetic analysis. That's an obvious thing to do. What she did was a behavioral experiment, or she put out all of these artificial caterpillars. That's the real thing. There's the spice bush swallowtail caterpillar. This one has got eye spots, that one doesn't, and she had certain treatments where they had eye spots and they're in shelters. This one doesn't, and that's a natural shelter like that. And what she found here is this, that the lowest attack rate or highest survivorship was for those that were showing eyes and they were just peeking out of the leaf like that. It was rather interesting. But there is another explanation, and the other explanation is maybe we're thinking about the wrong sort of predators. We're looking at birds. What about arthropods? Well, working with Carl a couple of years ago, we decided to do some work on mantids and spiders. And so what we did was present mantids of different sizes with a choice of mealworms with tiny little eye spots versus not, like that. And this is what we found. When there were small instars, the vast majority, if they went for anything, went for the no eye spot compared to the eye spot. But when they were much larger, it was much more 50-50. In fact, there was a tendency to take more of the eye-spotted ones than the non-eye spotted ones. And that was exactly the same with zebra spiders too. So here, it's relative size matters rather than absolute size. And if you're big, you can tend to be attracted to these eye spots. But if you're small relative to it, then you'll tend to be deterred. Okay, this is the final. Are we doing okay? Great. The final bit, the conjurer's tricks. So I've talked about these threat displays, but there's a subtly different form of display which is typically only revealed as you're fleeing. Here, an example is stick insects, when they're flying, can show this sudden burst of colour. Many grasshoppers will also show a sudden burst of colour. They're typically cryptic. When they're flying, they go like that. Birds, some of them will have certain feathers that look really conspicuous and yet that look rather dull when they're sat there. Hugh Cott, and the reason why I've called it conjurer's tricks, he said that they flash out during movement and vanish again like a conjurer's rabbit. And so these so-called flash displays have got a certain magician quality. Here's the Carolina locust that we've been working on. That's typically cryptic, really hard to find, but when you disturb it, it flies out, and I'll show you some video in a minute, really brightly coloured, and then it will settle down. I'm going to try, this is a very long video, I'm going to try and show you part of it. Let me just show you here. You probably can't see it. Oh, there it is. This is slow-mo photography. It looks a little bit like a butterfly, but believe me, it's actually a locust rather than a butterfly, and I'm going to return to that later. So, what are the explanations for that flash display? And by the way, males and females both have those flash colours in almost all those flashes. It's not sexually dimorphic, so it's not sexually selected for. Here's the most popular explanation that has been around for a long time. So let's say you see a fleeing prey and you see it's cryptic in flight. Well, you then look to where it's landed and then you look for it, but your search routine is basically tailored for the fact that you know it's going to be cryptic, so you're going to search for it for some time because you know it's going to be hard to find. However, what happens if you see something and you only see it in flight and it's conspicuous? You then go and look to where it landed and you're expecting to find something conspicuous, and so you will tend to give up sooner because, hold on, it's not there, it was bright red, I don't see it, it must be elsewhere. So you would search for a limited time because it should be easy to find. A few years ago we decided to put that to the test, and the way we did it was a simple human experiment where we had prey that moved across the screen, they flashed and then they settled in another part of the screen. Here's one here, just a little prey here. They moved to another part of the screen, you'd go and search for them, and then individuals would either give up because they can't find them, or they would find them and click on them. And here is the survivorship of the flashing prey versus the non-flashing prey. And so clearly there's something going on with that flash which really doubles the survivorship of these artificial prey. Of course, that's with humans, and quite recently we've been doing work with Chanku. Looks at chicks. Here you'll see, there it is. It's gone. There it is. It's gone a little green, but it's expecting to find that green thing, that red thing, and it's disappeared basically in front of its eyes. Whoops. So, it turns out you can model the phenomenon, you won't be that surprised. Imagine you're a bird and you see something fleeing and you think it's in one area, but it could be in another area, and there's a small chance it's in another area. So you've got your prior beliefs as to where it's landed. You'll search, obviously, to where you think it's most likely to be, and rather like looking for your wallet around the house or keys, you'll search in an area, and then if you don't find it, you'll think, oh, okay, I'm going to go, it must be downstairs, so you go and search downstairs. And if you search for it there and you don't find it, oh, mate, it's in the garage, and you'll go and search for it there. And of course, the more conspicuous it is, the sooner you should decide it's not there. Because if it's really conspicuous, well, hold on, I should be seeing it. It should be screaming at me in this room. I don't see it. It must be elsewhere. This is the basis, by the way, of what they call Bayesian search theory, and it's used all the time looking for sunken planes, or sunken subs, planes that have gone down. we follow simple Bayesian rules, and the theory of optimal search has been around for a long time. And quite recently, Carl and I decided to adopt Bayesian search theory to understand the evolution of these flash displays, because it follows really very similar logic. And the model, which I'm not going to show you, makes a number of predictions. And one is pretty obvious. The less confident a predator is that a prey is present, the shorter it should stay there looking for it. So if it's not sure if it's there, it's not going to spend too long. And we actually found evidence for this, because in order to get humans to behave in sensible ways, whenever we ran these experiments, we also had a number of duds. And the number of duds were individuals that fled, and they actually weren't genuinely there in that place where the human thought that they had settled. And it turns out the higher the number of duds in the training trial, the shorter the time before the search was abandoned, which fits perfectly. And here's another one, and this one's a stronger prediction. It says, the more conspicuous the flash display, the greater its effect in reducing predation. Because if you see something which is ridiculously conspicuous, when you look for it in the place you think it's settled, you should clearly give up that much sooner. We decided to put that to a test, and we actually found that if you have a flash display which is simply different but also cryptic, it will think, I'm going to look for a long time, or humans will think, I'll look for a long time before giving up. Whereas if they see it and it's really ridiculously conspicuous, then they'll spend much shorter time, and so the survivorship will be that much higher. So that fits the overall mechanism. But there's a third prediction, which is even stronger prediction, and it's that. The species with flash displays will benefit more if the predator is unaware of the prey's resting appearance. Obviously, if you know it's cryptic at rest, when you see it flying, when you go to look at it again, you're going to be thinking that's cryptic. And so we decided to put this to the test. And the way we did it, we manipulated something called the flight initiation distance. And again, this part here was with artificial prey. The flight initiation distance was how close the mouse pointer had to be before the prey went off. For low FID, basically the mouse pointer had to be almost on the prey before it fled, whereas high FID, the mouse pointer just had to move anywhere, and then the prey would flee across the screen. And only when individuals had, when there was a high FID, i.e. the human had no chance of actually seeing its resting state, did we see the overall effect. And then we did something else. We looked at Australian birds and the FIDs of Australian birds, where patterns had been sought to see whether there's any overall effects of anything. Patterns are really quite hard to find, but in this one, there was actually quite an easy one. We categorized the birds in terms of whether they had conspicuous signals or not, hidden signals. And then we looked at their FIDs. And what we found is bigger birds had longer FIDs, and so they left sooner than smaller birds, or in terms of the distances. But then there was an effect of whether they had flashing signals or not too. And the individuals with the flashing signals were spooked sooner, and they flew away at a shorter distance than individuals without it. Okay, so here's a question. Why look simply conspicuous when you can look like something which is not only conspicuous but hard to catch too? Because it struck us as other researchers that many of these individual flashes, especially in the Orthoptera, fly rather like butterflies. In particular, it's been alleged that the Carolina locust is actually a mimic of this very hard to catch species here, the mourning cloak. I'm not going to go into detail, but we've actually looked at a lot of flight data of the Carolina locust and compared it with the mourning cloak, but that will be for something else. Okay, so here is one example of a species, and you might think that that is a fly. It's not actually a fly. Here is a sarcophagid fly, This happens to be a weevil. And the argument from Van In and Guerrero is that the weevil gains its advantage by looking like the fly, not because the fly is unpalatable, in fact it's not. It's because this sarcophagid fly and flies, many flies like it, especially those with red eyes, tend to be very fast flyers. And so the argument is that the weevil is gaining some selective advantage by looking like the fly, not because of distastefulness, but because this is a highly evasive model. It means, if correct, we would have to change our view of what aposematism actually means. It's not unpleasant or dangerous, it's just simply unprofitable to pursue because it's so hard to catch. Now, the idea that you can have mimicry based on evasiveness is not new. It goes back to the 1970s, where there was a nice, simple experimental paper in Nature showing that it could work. And since then, there's been a number of really nice experiments. We've done some theory. This is a long time ago. But this is a subject of some controversy still. In particular, Andrew Brower wrote a very critical review of the evidence, arguing that it was very unlikely to evolve in nature, mainly because it's easy to put to the test. Any predator wants to know how good you are at flying, you can just try and chase you. And the second thing is, the argument from the available data at the time was that the learned avoidances of limited duration, and very quickly the birds will forget, they'll remember unpalatability for whatever reason much more. However, the tide is now turning because many tropical biologists are beginning to argue that there is a whole suite of butterflies out there which are not distasteful in any way, but somehow signal their unprofitability by being really evasive. And one example, although there's mixed evidence for all sorts of things in the blue morphos, is these. If you ever try to catch one in the neotropics, well, they're really hard to catch. And possibly the blue signals of the blue morpho is not anything to do with unpalatability, it's just, it's signaling it's hard to catch. It's cryptic at rest, and by the way, this is the other side. It's cryptic at rest, possibly, in my mind, because in the mornings it's a bit sluggish, and of course, if you're brightly coloured, you'll easily be picked off. But if you're cryptic, well, for cool temperatures, that's perfect. When it warms up, you're much more mobile, and you can signal your evasiveness. And not only that, but there's been a lot of work now on looking at mimicry rings within neotropical butterflies based on evasiveness rather than on palatability. I'm not going to go into it. So, recently there's been this big surge of interest, largely because of these field biologists that have been reporting very plausible cases of evasive mimicry. And here is an example recently of an experiment that was done. This is on blue tits. And you'll see that the blue tit is just getting a little bit annoyed because certain models here are really hard to catch. And yet others would be that much easier. And then, of course, you can introduce mimics that have most of the traits in common with the models. And the birds learn after a while, I ain't going to chase those, they're just not worth it, and only go for the easy to catch things. So another really great bit of evidence that evasive mimicry could work. Recently we decided, well, there's a few little issues here. One is possibly, although this looked pretty smooth, the sudden movement could startle, so maybe that movement itself is just putting the birds off. And here it was a real test of the extremes. They were either impossible to catch or possible. And in reality, if you've got evasive mimicry, maybe if you're good enough, you can catch some, but they're just hard work to catch. So we decided to also look at evasive mimicry, but we decided to look at evasive mimicry using mantids as predators. This is with Carl again. And what we did was this simple design. This is the last experiment I'm introducing, by the way. A simple experiment where we had 4 treatments, where in treatment 1, one type of fly with a white dot had its wings cut, so it was easy to catch. And the other type didn't have its wings cut, and that was black. And then we reversed it so that the black dot meant easy to catch. And then in treatment 3, both were easy to catch, and in treatment 4, both were hard to catch. So here, both had clips, and here, neither had clips. So I hope you understand that. And what happens? You basically throw the two flies in, and you get them used to, white ones are easy to catch, or black ones are easy to catch. And here are the training over the trials. It's not necessarily learning per se. The white clipped ones, the mantids were eating, there's 20 mantids, out of the pair, the vast majority were white clipped. And you'll see that it's from the get-go, so it's not necessarily learning, it's just the white clipped ones are easy targets, whereas the black clipped ones are, the black ones here are flying around, and the reverse is true there. And of course here, when neither are clipped, in the study time, there's quite a lot of no captures at all, because they're both really quite hard to catch. So after these training trials, and it was done on not consecutive days, this took 2 weeks, you then present 2 tethered individuals, a black and a white one, which are not clipped, but they can be caught, and you look at which one is caught first. It turns out that if they're used to the white ones being easy to catch, they prefer the white ones. If they're used to the black ones being easy to catch, they prefer the black ones, and it's pretty 50-50 in between. So here again, we've got evidence for evasive mimicry, but this time through a mantid. An invertebrate predator can learn some basic things, and these signals can be exploited, and so we've got evidence for that possibility of evasive mimicry. Okay, I'm going to summarize. Prey species are selected to exploit their predators' cognition. I think you all knew that anyway. Every species has its story, but we can see the importance of predator cognition through phylogenetic associations. For example, we're looking at associations between body size and whether they've got eye spots, etc. Defended species with hidden warning signals could potentially facilitate the evolution of permanent warning signals. We've done this with amphibia, and now, well, I can talk about it later, we're also looking at snakes and the possibility of that working in snakes too. Not all defenses have to harm the predator. They can simply be hard to catch, and their signals can be mimicked by species that are relatively easy to catch. And finally, another take-home message is that invertebrate predators that have often been overlooked, they can learn signal associations, and so also select for mimicry. Just a few people to thank. These are the main names that I've mentioned, but I just want to repeat my thanks to Alice for hosting us on this trip. And of course, I've got tons of backup slides. I'm really happy to take questions, but I think we're going to have a break first. I'm not sure. But thank you very much for your attention.